Please take a seat. We are about to start. So, good afternoon, everybody. We're going to go ahead and get started with our session 4, which is advances in accelerators. Closer to you, please. Accelerator technology for hadron therapy facilities. I'm the moderator. I'm Laura Vallo. I am a radiation oncologist at Mayo Clinic. I'm just pleased to be here and want to thank the organizers for allowing me to contribute. So our first speaker is virtual, and that is Alessandra Lombardi. Sandra, you may, yeah. Very good. Can you speak, please?
Yeah, hi everyone. I'm sorry not to be in person there with you in that what I imagine is a very nice place, and sorry not to meet you in person, chairperson. But I'll do my best from over here. So as you probably have heard, we have a little bit changed around the talk at the last minute. So I'm Alessandra Lombardi. I work in beam department, Accelerator beam physics, and in a section that is called Hadron Sources and LINAC. And in this section, we are doing we are following the CERN operational sources and LINAC. We are designing new LINACs and sources for various activity, and one of them is the activity for societal and medical application, which is the subject of this workshop. So what I'm going to tell you in this next 15-20 minutes that we are together is how we went from a necessity of our flagship collider, the LHC, to designing and successfully testing and producing and industrializing RFQs, so radio frequency quadrupole, for specifically medical application. So this is the outline of my talk. I will start from LINAC 4, then how this R&D was applied in medical and societal projects, and then a glance over few societal projects that we have been involved on. I think I don't need to go into the details. This is the CERN Accelerator complex, and I would like just to show you that LINACs are this little part just at the beginning of the complex of CERN ring. But LINACs, hadron LINACs, so what I have circled is the proton part, there is the ion LINAC here, are as well what really determines all the characteristic, and especially a parameter that is very important. I cannot change the page. Voila. That is very important for fundamental physics, that is the luminosity. So luminosity is this, let's say, formula with many factors in here. I'm not going to go into all the detail, but in the LHC luminosity, we can identify two factors. Part that comes from, let's say, the collider ring itself, and which are the optics interaction point, the limitation of the machine, the number of bunches, but then there is the brightness that comes from the injector. And the first chain of the injector is a linear accelerator. So I'll fast forward a little bit here the story to the decision that was made by our Director General in 2007 to renew the injector of the proton complex at CERN with a new LINAC. this new Linux, between the decision and actually the inauguration, was an adventure of 10 years, very successful adventure that ended up with the Linux being the sole injector for all the proton complex at CERN since 7th of December 2020, and with a Linux that nowadays nobody talks about because it works so well as an excellent availability and stability. You can see in the picture also Maurizio, whom I know is in the audience, and together with a bunch of other collaborators in several frameworks, and the last one is the NIMS. We had, together with the vision of our management, the idea of bringing the most important innovation of Linux 4 to the use also in other contexts, and in this case, medical and societal context. So what were the main innovation, or let's say the innovation that are relevant for this workshop? First of all, a technology for designing, bracing, operating a radio frequency quadrupole. And really the experienced use for the design of this radio frequency quadrupole was translated to, as you will see, the medical and societal field. A fast chopper that I will not talk about today, and a permanent magnet quadrupole. To give you an idea, normally in Linux facility, we have electromagnetic quadrupole, which means power supply, objects that can fail, objects that are very costly. With Linux 4, we did the experience of having the old DTL and part of the following accelerator using permanent magnet quadrupole. They were produced in particular in the European history, and they have been working very well for the last 5 years, also in a, let's say, radiation environment. Okay, so here it starts in 2014, the story of exporting this novelty, this technology, to medical application. Also in this case, I will tell the story a little bit fast. If you want more details, they are on the slide. So our first adventure was the study of an efficient accelerator in the range from few keV to about 5 MeV for Linux-based hadron therapy facility. I called this radio frequency quadrupole at high frequency that we designed, really the missing link between the source of particle and the high energy structure at 3 gigahertz. So this was designed at CERN. Sorry, it was designed, machine assembled, braced, everything at CERN. I report here the table with the characteristic of this radio frequency quadrupole, and I highlight here the frequency, 750 megahertz. It's a very high frequency for this type of machine, and it was the jump that allowed us to make this radio frequency quadrupole compact, and therefore very suitable for a medical facility. A few more pictures that shows the assembly, the tuning, and the high power RF. So you see the radio frequency quadrupole here. It's 2 meters in length and made out of 4 sections of 1 meter. It has to be handled very, very carefully. But once in place, it's very easy to operate. It doesn't need very much tuning or regulation. There is only one knob really to operate this machine. The test with this RFQ were successful. So we had a low energy pre-injector, so with a standard source an RFQ, and then some diagnostic. And this allowed us to validate here at CERN back in 2017, this radically new design from the beam dynamics point of view that was then validated with beam measurement. Okay, so then we validated this first jump to a high frequency, and then a few years later, in about 2019, we started designing, and in 2022 you can see already the picture of the beam out of it. We further developed this technology, and we produced another radio frequency quadrupole, this time for use in the art diagnostic with the PIXE and PIGE technique. And what we have done here, it's okay, an RFQ that is even more compact, and the reason is that we need only an energy of 2 MeV for this application. But in particular, we have reduced the voltage that we need inside our RF cavity to about half what we need for medical application. And this jump, beside allowing a certain saving in power, it allows thinking about portability. So an object that is not only compact in itself, but also that needs a power that is not that doesn't require a very heavy installation. We can imagine an object that we can, I would not say yet easily, but that we can move around. And this is particularly important for this type of application, because a lot of times we have a fresco or other type of art form that we cannot easily move to a center. I was talking also about permanent magnet quadrupole as one of the interesting innovation that we could apply to other fields. And here I show you we have after the RFQ a very simple system, if I may say, of permanent magnet quadrupole that we can actually physically move to change the beam size. It's a little bit like a telescope that we can, focus at different distances. So by carefully choosing the position of this permanent magnet quadrupole, we can actually change the beam size from 400 microns to 35 microns to 20 microns, just changing the relative position of these two objects. Just wanted to say that all what we did actually worked. What you see in this picture is the image of the beam, the fluorescence of the beam in air that our colleagues from INFN Florence produced. And let's see if it works, that I move the page. And by changing the quadrupole, you see, we can actually change the aspect ratio of the size of the beam almost, live as we need it. Okay, sorry, I don't take you through the movie. You can click it and watch it yourself, because for sake of time, I want to go to the next subject and say that that we have basically an equivalent system as the one that is called Machina, that is now sitting in Florence. An equivalent system is called ELISA, so Experimental Linear for Surface Analysis, always 1 meter long, as you can see, that is hosted at the Science Gateway, the new visitor center of CERN, and is used as a demonstration, as an experience to the public with the beam that will be able eventually to play around with quadrupole and change the beam size and see also much more than just that, see all the techniques for learning about diagnosing objects, art objects. Okay, now coming to the development that we are doing, the latest development that are still a work in progress. So the next challenge is to accelerate carbon ion in a LINAC. As you have heard from Maurizio this morning, he was saying that the first step in this project is to build and validate a pre-injector. And this is exactly what we are doing with the development on the source and the low energy beam transport that you will hear from my collaborators, Aris and Amer in a moment. And the testing of the radio frequency quadrupole for carbon. And let me spend a couple of words on this. So this is a result of a very successful collaboration between CERN, CIEMAT, and the Spanish industry. So we see the radio frequency quadrupole for carbon is 2.5 meter long at 750 megahertz that will deliver carbon or, for what matters, helium alpha particle at 10 MeV. And if you wanna see the latest news from the test stands, these are pictures that I took this morning. You can see the source that will be used for the initial test of the RFQ. In blue here, the table where the RFQ, that is at the moment still in a box, will be housed on Monday to proceed then to RF conditioning and setting up for beam test. So what's coming up? So we, as I said, we have a source designed to inject directly into the RFQ. We have a helium source and a low energy beam transport. As I said, you will hear some details in a moment. The RFQ designed to accelerate particle with charge over mass 1/2, so be it helium or fully stripped carbon ion. And with all this, we will characterize the proton and the helium sources for use with this RFQ, accelerate the beam to the RFQ, and hopefully validate this new RFQ design and proceed to the construction then of the second RFQ or NIH structure to further increase the energy. And to conclude, if you allow me one more minute, I wanted to put on just one page the development of RFQ at CERN and the path from, let's say, something that can be built and operated only in a laboratory to something that can be industrialized. If we look at the 1990s, we had a proton injector in RFQ at the frequency of 200 megahertz. Okay, so this is an extremely bulky object. I let you read all the details. Then with LINAC 4, we already made a frequency jump of almost factor of 2 because the technology allowed and all the R&D allowed. And we gained both in weight and in the, let's say, accelerating rate. Big jump came when we made an RFQ at 750 megahertz, so another jump of factor of 2 in frequency that allowed the RFQ to be compact. And then with Machina ELISA, about a few years, 3-4 years later, we could make the RFQ portable. And then with this RFQ for carbon, we really were able to streamline both the design and the construction so that it could be industrialized. So over a span of 30 years, and with the occasion that we had to reuse all the knowledge of the RFQ2 and the RFQ of LINAC 4, we could definitely bring this machine into something that is useful and usable as well in societal and especially medical application. So this is all I have prepared today, and I'm ready for any question you may have.
Thank you, Alessandra. Great talking. Thank you for being on time. Any questions from the group? Yoda?
Hi, Alexandra. This is Jota. It's not a question, just to thank you and thank all the colleagues at CERN that you are somehow acting as mentors for the young students from Greece, from Sarajevo, from Montenegro. There was a big discussion in the morning about capacity building, and I think we are grateful for the time and effort you put in this project. Thanks a lot.
Okay, thanks a lot, and you'll hear from them in a moment. I see from the program.